Hello, my name is Tokunaga. That is my student ID. And my presentation is about 3D printing of living tissue, which is also known as 3D bioprinting or bioprinting. Bioprinting is an emerging field in regenerative medicine. It's an extension of additive manufacturing that involves building a tissue or organ layer by layer using the bottom-up approach. Now, bioprinting can provide patient-specific spatial geometry, controlled microstructures, and the positioning of different cell types for the fabrication of tissue engineering scaffolds. Its main objective is to mimic natural cellular architecture by depositing materials in cells to restore the normal structure and functionality of complex tissues. For the 3D bioprinting process, to begin with, imaging modalities such as CT, MRI, or ultrasound can be used to create a digital 3D model of a tissue defect interest. We can then, it is followed by using computer-aided design, from which the internal and external architecture of the scaffold, such as porosity or pore size, can be incorporated into a 3D model of the tissue defect. And then we, in consideration of the defect type, and requirements, a selection of materials, cell types, and bioactive molecules can be used to fabricate a bioink for printing, which is very important to remember, the bioink, which I'll follow into that later. Cell-laden structures are then manufactured using bioprinting technology and are then placed either in a cell culture or directly implanted into a patient. This is a visual schematic diagram of what I just said. You have an organ or tissue of interest, 3D imaging, then you go to the CAD model, generation of G-code, then you select the materials and cell types for a bioink, and you do the bioprinting, then you have a cross-section and complete allogeneic heart scaffold in this case. Now, something very important, as I mentioned, are bioinks. These are biomaterials that can be used to encapsulate cells and incorporate biomolecules. Its main properties are viscosity, gelation, and cross-linking capabilities. These properties can significantly affect print fidelity, as well as cell viability, proliferation, and morphology after printing. We have 4 bioprinting techniques, which I will briefly describe in the next slides. First one is inkjet-based 3D bioprinting. It uses a heated element to nucleate a bubble. The bubble causes a buildup pressure within the print head, which leads to the expulsion of droplet. It's a non-contact printing technique. It allows for the precise positioning of cells, which are patterned using the droplets I mentioned. It has high print speeds, low cost, and wide availability, but it has low droplet directionality and unreliable cell encapsulation due to the low concentration of ink. We're followed by laser-assisted 3D bioprinting. In this case, the lasers irradiate the ribbon, which in the schematic diagram is also known as donor slide. It causes the liquid biological materials to evaporate and reach the receiving substrate in a droplet form. It has a high degree of precision and resolution, but it is expensive and a time-consuming technique. We're followed by extrusion-based 3D bioprinting. The bioink is extruded through a nozzle driven either by pneumatic or mechanical pressure and deposited in a pre-designed structure. It has the ability to print very high cell densities, which is very beneficial. But unfortunately, the cell structure may be distorted due to the high shear stresses induced during printing, and it also has limited resolution. Finally, we have stereolithographic-based 3D bioprinting. It uses UV, or visible light, to cure photosensitive polymers in a layer-by-layer fashion. It has a high degree of accuracy with low printing time. But unfortunately, it has lengthy post-processing and it is a highly complicated process. Now, having this mentioned, we have advanced applications using this technology. Great efforts have been made in developing bioprinting technologies to attempt to print blood vessels, heart, bone and cartilage, kidneys, skin, nerves, and other tissues. Now, for some applications of what I just mentioned, for blood vessels, we can optimize vascular geometry and cell viability and function. For heart, we can print valvular interstitial cells into scaffolds with high speed and good viability. With bone and cartilage, we can build scaffolds to provide a framework for the cells to attach. For the liver, we can make biological livers for a liver transplant. And also we can build liver tissue if it is ever damaged. And finally, we can make skin substitutes to repair skin wounds. And also, very importantly, we can study pathophysiology of skin diseases. Now, of course, it also has its challenges. First of all, we need suitable bioinks. As we know, well, as I mentioned, these are very important, but it is also, you also need like a specific bioink for each specific application. So you need to take that into consideration. There needs to be suitable bioinks with good biocompatibility and mechanical strength that can be used to achieve biological function. We have to also ensure suitable mechanical properties of what we make, because, for example, during heart tissue repairing, porosity and structure designed by 3D bioprinting should maintain a high elastic modulus so that they can support the natural cell growth during implantation. So if the product doesn't have the proper structural maintenance and mechanical support, well, the newly formed tissues will probably fail. We also need proper vascularization in vivo and integration of functional vasculature in the grafts to ensure long-term survival. Different tissues of the body have different requirements of cell densities, number of different type of cells, temporal distribution of cells inside the constructs. Now, having this mentioned, of course, there are future aspects to be considered from which 3D bioprinting will probably develop. It's looking to develop, it's working on it. First of all, I'd like to mention that combining techniques is one of them. As I mentioned, they all have their advantages and limitations. So what people are doing right now is taking the advantage of one and combining it with the advantage of another one and making a product. Because you cannot use just one technique for every application. Yeah. Also, over the recent years, new techniques have also been in development. These include, among others, procedures that involve magnetic and acoustic-based printing, electrohydrodynamic processing, and also new methods for the 3D patterning of spheroids and organoids, for example. Also, very importantly, there's also great potential in replacing animal studies for drug and material screening. This is very important because, well, for example, I don't know, I just made a product and I need to test it, and I need 1,000 rats. But with this 3D bioprinting, you don't need those 1,000 rats. You'll just print out, I don't know, the liver you need for testing, the 1,000 livers you need for testing, and that should work. Finally, there's also potential to provide pre-vascularization of the scaffolds. As I mentioned, it's also a challenge. So people are looking into it to solve this. Because pre-vascularization is essential to avoid necrotic failure of the implantation. Well, as we know, it's a new technology. Well, it's an up-and-coming technology, and it is expected to overcome the challenges in the near future. Thank you very much.